And with me, yeah, I will not.
Oh, it's a bit. Oh, okay. Yeah. Well, thanks for inviting me, and I'm here to talk about the COVID-19 vaccines. And since we don't know a lot about COVID-19 vaccines right now, it's going to be a general talk about sort of post-licensure studies of vaccines with respect to safety and effectiveness, and some of the many unknowns that we will have to be looking at with respect to the hopefully coming COVID-19 vaccines. And so this is I mean, it's very easy to find a lot of nice infographics on the internet now when you Google COVID-19, and this is one I picked up, and it shows sort of the very accelerated vaccine development schedule that we've seen for COVID-19. It's very extraordinary, and here you can see sort of a typical 16-year period, almost here, an estimate of that for a typical vaccine, going all the way back to academic research, preclinical workup, and in human studies, and then building factories and getting approval and then distributing the vaccine. And we live in very extraordinary times, and this has been accelerated extremely here in 2020, as you can see from the beginning of year, where we learned about COVID-19, and to now, where we are apparently only months away from efficacious vaccines. And for those who don't know a lot about the development phases, I mean, in the pre-licensure phase, before we get to the observational studies, before we get to use the vaccine in a large population, I mean, we have to start out with academic research to develop a vaccine candidate. And as some of you may remember, back in 2004 or 5, we had a SARS. So already back then, a lot of research groups started working on a vaccine for a similar virus. However, since SARS was quite well controlled, it's practically eradicated. I mean, there wasn't really any financial incentive to go further with a vaccine candidate at that time. But a lot of academic research was done back then, which is benefiting this accelerated process now. And also a lot of the academic research is founded in you know specific vaccine technologies, which I will come back to. So that phase has been accelerated quite a lot. Then we have the preclinical phase, where we test the vaccine candidate in lab animals, in mice, in chimpanzees, to see if it's toxic, to see if it produces an immune response. We conduct challenge studies, and then we move over into the human subject studies, the phase 1, 2, and 3 trials. And here, I mean, phase 1, phase 2 are sort of overlapping to an extent. And phase 1, we start out with something like 10 or 20 people, and just studies of, again, toxicity, basic safety. Does it produce an immune response? And also we need to start thinking about what is the dose going to be for this vaccine. So we may do a dose escalation study to sort of see where is the balance with respect to adverse events and immunogenicity. Again, some of the same things we are looking at in the phase 2. We may be characterizing the immune response a little bit better there. Also looking at safety. Affected 10 more people, I would say, normally. And then we move into sort of the final clinical trial phase, the large phase 3 studies. And we've learned here in the COVID, with respect to COVID vaccines, that we are talking about clinical trials of up to 30 to 60,000 people. And the main objective here is to determine efficacy. of the vaccines first, and also to look at safety in a bigger scale. So having done all that and all these studies, very expensive studies, why do we even need to do any observational research? I mean, my claim is, as an epidemiologist, that it's very important, of course, and that's because I mean, the real world setting in many ways doesn't equal the clinical trial setting. And if we look at sort of the two important characteristics of a vaccine, effectiveness and safety. Effectiveness, I mean, in the clinical trial, you have a very well-defined outcome that you are studying for when determining efficaciousness. In these trials, they're probably looking at PCR positive with symptoms as an outcome. But in the real world setting, we may be interested in knowing about the effectiveness against a number of other manifestations of the disease. It could even be down to asymptotic infection, severe disease resulting in hospitalization, eventual death also. And there's no sort of reason why we should be able to sort of predict these from the clinical trial data. We'll have to study them in the real world setting. Duration is also very important for how effective a vaccination program is going to be. Again, the very accelerated schedule and the fact that we'll have to license these vaccines on an emergency use basis means that we won't have that much duration in our clinical trials. So we won't know how long immunity is going to last and how it wanes over time. We will be interested in the real world setting in specific subgroups. I know that the different companies have sort of recruited elderly, given the specifics of who are at risk for COVID, severe COVID-19 disease in their studies. But again, perhaps they haven't recruited enough to be able to do high-powered subgroup analyses, or they have probably only recruited elderly who fulfill a lot of inclusion criteria, which probably excludes a lot of the elderly who have a lot of comorbidity and are at high risk of developing severe outcomes. Again, logistics, especially with some of the new vaccine technologies, as we heard with the Pfizer vaccine, that we have some storage issues. We need minus 70 degrees Celsius storage for the mRNA Pfizer vaccine. Again, herd immunity. It's also relevant, of course, for vaccination. It's been brought up a lot this year in terms of how to control COVID-19. It's also really important in the vaccination program to vaccinate enough people so that we stop transmission to those we don't vaccinate. Again, uptake, how is it, how many are getting vaccinated, and are they adherents, are they getting vaccinated according to schedule? Again, if these things don't match up perfectly, like in the clinical trial setting, we may not get optimal results in the real world setting. And again, over a longer time period, what happens when we start introducing a vaccine in the sort of the epidemiology of the pathogen, the ecology of the pathogen. For example, we know from some bacteria that we could perhaps fear that there'll be some, when we remove one pathogen, that there will be sort of a replacement pathogen entering this ecological yeast. For safety outcomes, even though we have quite large clinical trials with 3 trials, rare events are still something that we have to look at in the real world setting. One of the trials was put on hold or paused due to transverse myelitis, which is a quite rare event. And they wouldn't be able to sort of study it analytically with any statistical power in the clinical trial. Delayed events that occur more than months after. Subgroups again, for example, pregnant women is always of great interest, even though we don't recommend, or I don't expect that any of these COVID vaccines will initially be recommended for pregnancy. If we're going to vaccinate larger parts of the population, we're probably going to vaccinate some who are not inadvertently pregnant, but we are going to inadvertently vaccinate some who are pregnant very early on and don't know it yet. Again, there's this issue of the placebo, that many of these clinical trials probably doesn't use a saline placebo, which is a bit of a red flag for the anti-vaxxers. Instead, not as a great conspiracy, but to ensure double blinding, they use in the placebo group another vaccine or perhaps an adjuvant without an antigen to produce an immune reaction, so that you get sort of the same local reactions, maybe a slight fever, and so you don't suspect that you haven't gotten the vaccine. This shows sort of the many different types of vaccines that we have in this race for a COVID-19 vaccine. We have old technologies and new technologies here. The whole virus vaccines that are being developed are mostly what I've heard from Russia and China in form of an inactivated. This is simply just, you kill the virus and inject the whole virus, the whole killed virus, or you can have a weakened version where you attenuate the pathogenicity of the virus, like we know with the measles, mumps, rubella childhood vaccines, for example. Then we have the vector vaccines. These are the so-called Trojan horse vaccine, which sort of carries the COVID-19 antigen gene in a non-pathogenic viral vector. And then we have the DNA and RNA vaccines, where you inject the DNA or messenger RNA, and you make the body's own cells produce the antigen and then develop a response against it. And the protein-based vaccines are sort of where you purify the protein. In the COVID situation here, it's the very famous now spike protein, surface spike protein, probably. And we also have many of these vaccines in our programs right now. But for the viral vector vaccines and the DNA and RNA vaccines, these are quite new technologies. We don't have a lot of experience with them in humans. So that's also really interesting to follow the vaccines. This is the Danish situation. This is what we are probably going to have to be working with for the next 6 months. This is the Oxford vaccine, which I heard was yesterday. They reported an efficacy, an interim analysis efficacy of 70. And then the Johnson & Johnson and the Sanofi, they haven't revealed anything to my knowledge. And then we have the Pfizer, which is the messenger RNA, which also reported on an interim analysis, an efficacy of around 95, I believe it was. And that's the vaccine that has to be stored at -70°C. I've written doses here. It wasn't actually clear to me whether these reports from the Medicinal Products Agency refer to number of people that they were able to vaccinate, or number of doses. That's quite important, actually, because I mean, for many of these, we are talking about 2-dose schedules. But again, we are waiting on the Ministry of Health and the Board of Health to reveal the Danish vaccination strategy, which ones are getting which vaccines first. When we're talking about effectiveness, we are generally defining it as sort of a relative risk reduction. We can estimate it as 1 minus the relative risk, 1 minus the rate ratio, 1 minus the odds ratio. We may want to talk also in absolute numbers and talk about the absolute risk reduction, and talk about how many do we need to vaccinate to prevent one case. Different epidemiological studies that we can use. The cohort study, which is a Danish favorite, where we have our registers. And it will typically be used in a setting where we have an outcome that we want to look at that is well registered in a nationwide register, some sort of hospital outcome, for example. A case control study design. In this case, we often use what's called a test negative design, which I expect will also be used here in the COVID-19 situation, where we are interested in determining effectiveness against an outcome in the lab setting, for example, the PCR positive test. And there we have to, there we are trying to avoid some selection bias by comparing test positives with test negatives. So restricting the study to those who are tested. A household context study, where it's sort of a challenge study where you have index cases in a household, and then you look at how many household members get sick. And then you can calculate the effectiveness from the attack rates. A screening study is used in a situation where you don't have nationwide detailed level data easily available, and you can calculate the effectiveness from the proportion of the cases who are vaccinated and the proportion in the population who are vaccinated. And typically in many countries they have reporting systems for infectious diseases, where it's mandatory to report certain infectious diseases, and there it's also mandatory to report the vaccination status. So when you have a system like that, you easily have the proportion of cases vaccinated and probably also some estimate of how many in the population receive the vaccine overall. And let me move into some examples of some of these characteristics of effectiveness. One of my own studies, an old study from 2004. This is an example of a cohort study of effectiveness, where we looked at hip vaccination and hip meningitis, a sort of in the childhood vaccination program. And we conducted a study of 500,000 Danish children, and had registered information on their hip vaccination status and whether they were hospitalized with hip meningitis. And what we found was a very, very high vaccination effectiveness, as you can see here in the table. So that was a very successful vaccine, at least in terms of sort of one of the more feared outcomes that it was supposed to protect against. One of the reasons that it was so effective was also that it introduced a high degree of herd immunity quite rapidly. And this is the figure that you see to your right. And this is, again, in the cohort, the comparison of those who remain unvaccinated after the vaccine was introduced, and the time since the introduction. So these are unvaccinated children compared to unvaccinated children before the vaccine was introduced. And you can clearly see that a rapid increase in herd immunity occurs that is comparable to a vaccine effectiveness of at this time point of over 90%. So that had a profound effect on herd immunity. Again, there are many reasons that we want herd immunity in the childhood vaccination program. We want to protect the infants who are not fully vaccinated. For many of the pathogens that we vaccinate against, they are only fully vaccinated at 1 year of age. We may want to protect those who cannot receive the vaccines themselves. Or there are other situations, for example, in the HPV situation, where vaccinating all the girls would protect the boys from getting HPV and subsequent cancers. Another important characteristic of a vaccination program is waning immunity. One of the sort of the challenges of infectious disease controls is pertussis. We've had pertussis vaccination since the 60s. We haven't been able to control pertussis. And one of the reasons for this is that we have waning immunity after both natural infection, after the old reactogenic whole cell pertussis vaccine, we had waning immunity, and also after the newer, more sophisticated acellular vaccines with a better safety profile, we also have waning immunity. And on top of that, when you introduce a vaccination program, you have less environmental boosting, which then is quite important when you have this waning. And again, this becomes quite problematic for the infants who we are only able to protect through vaccination when they are 1 year of age. So there's a lot of pertussis circulating. In the older populations, in the older children, it's asymptomatic, but it manifests as severe disease in the infants. This is a study where we tried to sort of see how could we indirectly measure this waning immunity to sort of answer the question, should we boost pertussis at 5 years of age, as was commonly suggested? Sorry. And this is a study where we looked at index children and living with older siblings, and looking at what is the risk of getting hospitalized with pertussis conditional on the age of your older siblings. And we saw this very striking result that there was sort of this peak among the older children, which could be which looked a lot, which was very compatible with this concept of waning, the fact that even if they're vaccinated, their immunity has waned, and they may not get asymptomatic disease in this age group, but they transmit it to their younger siblings. So these are some of the characteristics that we are able to look at in the effectiveness settings, and that we need to look at in the effectiveness settings that we don't get from the clinical trial setting. Again, a short example of the test negative design, also looking at some aspects that you're only able to look at in the real world setting with influenza vaccination of pregnant women, which is recommended. Here we use the test negative design to compare the influenza virus positive, PCR positive cases with the test negative controls. What's interesting here is that we we consider vaccinated pregnant women, but also consider their infants. So these are infants to mothers vaccinated in pregnancy, and we find reasonable effectiveness estimates for the mother herself, but also her child in the first year of life, compatible with transmission of maternal antibodies, or perhaps just a less transmission overall due to being vaccinated. Safety, also a very important aspect. Here I mentioned the self-control case series method, which was developed for vaccine safety studies, and which I think will be used quite a lot in the coming safety evaluations of COVID-19. You can sort of think about it as an individual stratified cohort analysis conditional on having events, and where you don't right censor at event. And it's sort of a comparison of rate ratios in different periods. For example, you often define a risk period of special interest, and then compare the event rate in each individual with event rates in other periods. For example, the period as unvaccinated, or perhaps also the period as vaccinated, but after the risk period. It's statistically very efficient. In many settings outside of Denmark where you don't have a full cohort, it's much more feasible. Since it's individual stratified, you take account of the time independent individual level factors. Of course, you have to do it in scenarios where a risk period makes good sense. And there is an R package that you can use for this. I'm quickly running out of time, so I will jump forward and maybe say a little bit about the vaccine safety. I've done a lot of vaccine safety studies. The vast majority of them have been negative, and it is sort of negative studies that you often do, fortunately. It's often not very well established scientific hypothesis you're testing. You're trying sort of often to counter many of these spurious anti-vaccine myths that occur. So it's always a question about which hypothesis do you test. When do you actually consider a vaccine to be safe? What does it even mean? And also think about what does a negative result actually even tell us. There are some quite specific vaccine safety challenges for COVID-19 that I want to mention here at the end. Since we don't have any experience with them, we won't know at the beginning which adverse events we're going to look for. We have to be able to respond quite quickly, I think, and we also have to think about vaccine-enhanced disease as an adverse event. That's the case where prior or being vaccinated doesn't protect, in some individuals doesn't protect against the disease, but actually makes the disease more severe if they get it. So we will have to be looking into real-time or almost real-time monitoring of safety. Here I have a method that has been effectively used in the US in their vaccine safety setup. It can be easily adapted to any study design. It's basically just a likelihood ratio test called the maximum sequential probability ratio test. Again, we don't know which adverse events to look for, so maybe also data-driven signal detection could be interesting. Another approach also that has previously been used in pharmacovigilance and also in the vaccine safety analytical space is the tree-based scan statistic, which sort of utilizes, for example, like many of you know, in ICD-10, for example, this hierarchical nature of the diagnostics coding schemes to get so that we don't get sort of this massive penalty, for example, when multiple testing using a Bonferroni correction. We are also going to have to look at this globally and try to make some common protocols for vaccine safety and effectiveness evaluation to enable comparisons between countries. Maybe we can use other countries to validate if we detect a signal. And again, combined analysis and meta-analysis of rare events and comparing vaccines will be important globally also. And I think I've run out of time now. Yeah, but again, the main take-home message is, of course, that they're very, very important that we do these observational studies to ensure that we have a safe and effective vaccination programs.
Thank you, Anders. Really, really enlightening and well timed. Being the chair, I can force myself ahead of the question queue, which is not supposed to be many questions, but I have this one burning, and I might not be the only one. The last couple of days, we have seen the Pfizer vaccine having effect above 94%. And then the AstraZeneca that was 70, and a few days later it was above 90. now I show my ignorance. When they state those numbers, what is it actually? What is being divided by what?
Yeah, it's not that clear. For example, whether it's a lower confidence bound or something that they're reporting. It's based on relatively few numbers and interim analysis. So this is sort of science by press release, it's called. I mean, we are really waiting on some more detailed reports now, publications preferably.
But I was actually thinking not so much the statistical part, but just what is it a percentage of? If one forget about the uncertainty and just say 90% of what?
It's
is that clear?
Relative. Yeah, it's the relative reduction in PCR positive cases.
Relative reduction in PCR positive cases.
Yeah, I would suspect that. Yeah.
Okay. Yeah. Well, thank you. This is actually a really great lead-in to our next speaker. Anders, if you could unshare your screen, thank you. Our next speaker is Samir Bhatt from, luckily and to our great privilege, from the Department of Public Health here at the University of Copenhagen from the 1st of February. Right now and recently he is at Imperial College, where he's been doing a lot of the disease spread modeling for the in the British setting and as a guide, as an external expert for the British government. I have this idea that these models might be even more useful now when we have to test out new vaccine strategies. But I should, of course, not put words in your mouth, Samir. So I also saw you had maybe a comment to the question I asked for Anders.
Yeah.
But the floor is yours.
Yeah, my question for Anders actually was again about this Oxford vaccine. It's slightly worrying because